What if there was a cost-efficient and more profitable manufacturing process that allows designers and engineers to utilize sculptured aluminum panels that are structural as well as ornamental? That revolutionizes the bridge building industry by replacing high-maintenance steel components with more affordable and efficient materials of lower maintenance requirements. That reduces construction time and lowers costs for mass transportation tunnels made of large structural panels, and makes possible the net shape forming of large aerospace parts for both military and commercial applications. Well, the future is here. Introducing the next generation in metals manufacturing technology, Meleform, a proven process that can fabricate components faster than machining, more accurate than conventional forging, and still maintain lower costs. The Meleform process squeezes material in a progressive and sequential motion that gradually compresses material to completely fill a female die cavity of a desired shape. A Meleform die consists of a lower female half and an upper male half. The male portion is made up of segments where each segment can move independent of each other. The Meleform process fabricates structural parts with minimum material waste, less flow time, and enhances the structural integrity of net-shaped parts. Meleform technology created this part, weighing 0.95 pounds, from a blank weighing only 1.06 pounds, resulting in 3.8% scrap. If this same part were machined from thick plate stock, 5.12 pounds of material is required, resulting in 81.4% scrap. Starting with equal weights of stock material, machining produces one part and a large volume of scrap. The Meleform process produces 4 parts and a small amount of scrap produced as flash. The Meleform process is more rapid and more material efficient when compared to machining. Conventional machining produces over 26 million tons of scrap each year. The production of a typical aircraft part using the Meleform process begins by placing an aluminum blank for parts with flanges on one side. A steel cover plate is positioned over the aluminum blank. The male segments are then positioned in place within the female portion of the die. The die assembly is placed in a furnace and heated to a predetermined temperature. The Meleform process has made prototype subscale parts from aluminum, lithium aluminum, and metal matrix composites. The Meleform process can also be used to shape titanium and titanium matrices. Upon reaching the desired temperature, the die assembly is moved from the furnace and secured to a hydraulic cylinder. As the male segments come in contact with the inclined surface, each segment is gradually forced down, shaping the heated material to conform to the contour of the female cavity. The hydraulic cylinder pulls the die assembly, encased in a die holder, past the inclined surface at a rate that is suitable for the material being formed. After the forming process, the male segments are gradually raised from the female cavity by an extraction ramp. At the extraction station, hydraulic pressure is used to eject the finished part. The black coating on the part is the high-temperature lubricant required to reduce friction between the aluminum being formed and the steel die surface. After removal of flash and surface lubricant, the finished part is net-shaped and has an RMS surface of 32, with no surface machine marks. The many types of aluminum formed with Meleform so far have been pulled at rates varying from 6 to 10 inches per minute.
The results of the Meleform process has been demonstrated on this prototype equipment. The results are rapid, repeatable, and offers capabilities not available in existing processes. Now, in addition to the material and labor savings you see here, engineers and designers can focus on increased physical properties, especially improved resistance to premature failure due to fatigue. We feel that in time, the Meleform process will gradually replace a significant portion of machining and conventional forging operations.
The metal forming manufacturing development, known as the Meleform process, which you have just seen, was funded by DARPA, also known as the Defense Advanced Research Projects Agency. This work was performed in cooperation with Pratt & Whitney Research in Florida. You are about to see several brief case studies involving other aircraft manufacturers. Case study number 1, Pratt & Whitney. The development of the Meleform process was advanced through funding from a DARPA Small Business Industrial Research Grant Program. The work was performed jointly with Pratt & Whitney Research Department. We concentrated on half-hollow fan blades, a very expensive operation. According to Pratt & Whitney personnel, the buy-to-fly ratio with their then current method was 10-to-1. After analyzing the results of the work performed using Meleform technology, Pratt & Whitney projected the buy-to-fly weight would be approximately 1.21-to-1, an amazing reduction. The half-hollow blade on the left contains the flash, while the half-hollow blade on the right has the flash removed. All the parts you see here were made on the prototype Meleform press. They are net shape with a surface finish of RMS 32. All are designed with a flash to ensure complete forming of the part. All half-hollow turbine blades require diffusion bonding followed with a twisting procedure to achieve final shape. A large percentage of turbine blades fail at the diffusion bonded surface. Using the Meleform process, we have been able to form half-hollow blades with a twist included to minimize strain after twisting. Case study number 2, Wyman-Gordon. A very significant case study shows how the Meleform process can revolutionize the manufacturing of large aircraft parts. The Wyman-Gordon 747 wing beam shown on the screen was forged on a 50,000-ton Wyman-Gordon press. After forging, the weight of the beam was 3,750 pounds. After machining, the finished weight was 825 pounds. This resulted in 78% scrap material. The machining took 213 hours. Documentation is available on request. The Wyman-Gordon forging process required a total of 6 operations: stock, heating, cog, and then 3 forming dies. The next chart shows the procedure for making the Boeing 747 wing beam from flat stock to finished part using Meleform technology. The time in the Meleform press will be just 2.5 hours. No machining will be required beyond the removal of a small amount of flash. The part will be net shape with a RMS 32 surface finish. Case study number 3, Alcoa. Alcoa was the leader in making large forged parts considered to be precision. It is very difficult to make precision parts with multiple flanges using the conventional forging presses. The Meleform procedure can produce parts of varying lengths, varying flanged dimensions, and with negative or positive draft angles. Working with Alcoa years ago, we received drawings of several large aircraft parts to estimate the Meleform process in manufacturing costs, including die costs. The chart shows 3 such parts and also an open view of one of the die designs used to make such parts. We prepared a summary report on the costs and feasibility for Alcoa. This 38-page report is available upon request. Case study number 4, an original request by the U.S. Air Force. Many years ago, the leading forging manufacturers were asked by the Air Force to combine their efforts in an attempt to design a 200,000-ton press. The Air Force's intention was to forge near-net-shaped parts to reduce subsequent machining operations, reducing scrap and material costs. In addition to the unbelievably high estimated cost at that time of $500 million, the group also advised that it was not feasible to make such an investment. The continued development of the Meleform process over the last several years now makes it possible to achieve the requirements that the Air Force was looking for. The principle of the Meleform process does not require the massive forces used in conventional forging presses. The Meleform press utilizes an inclined surface and segmented die to obtain the forces required, which are much lower than the loads required in traditional forging presses. This chart shows that a Meleform press can service dies of any length. The results will be net-shaped parts. All parts coming out of segmented dies processed on the Meleform press will require no machining except for holes and slots and removal of flash. Case study number 5, Boeing aircraft. George Nielsen and other Boeing engineers had long considered making monolithic parts by machining from large billets of material, probably resulting in 50 to 75% machined chips or waste. The Meleform system now makes it possible to fabricate large monolithic parts without machining. All prototype parts fabricated by Meleform technology using several high-strength aluminum alloys are all net shape. The Meleform process for manufacturing monolithic structures will lead to many other industrial applications. One example shown here is the monocoque modular all-aluminum bridge. It will have no rivets, no gusset plates, no trusses, and no catenary. Another example is a system of capturing the wind without large, expensive, and inefficient fiberglass blades, which are inevitably purchased from many foreign countries. In its stead will be the unique aluminum isogrid panel, which will capture the wind more effectively than large fiberglass blades. This system is patented in the United States, and everything will be made right here in this country, creating thousands of jobs. We have additional information and documentation available upon request. Future applications of Meleform technology: wind energy systems, wind energy recovery systems utilizing fiberglass blades have been receiving unbelievable government subsidies since 1992. The fiberglass design lacks efficiency and is expensive to fabricate, deliver, install, and maintain. Recent records show approximately 14,000 turbines have been completely abandoned. A group of 10 U.S. senators recently sent letters to their colleagues Max Baucus and Orrin Hatch in an attempt to terminate the production tax credit, thereby saving U.S. taxpayers millions of dollars. Meleform has patented an isogrid panel system that is more efficient and will not require government financial assistance. For example, the air utilization of existing 50-meter fiberglass blades is just 6%. An all-aluminum Meleform isogrid panel has an air utilization of 34%. A 15-page brochure is available with more information. It is reported that fiberglass turbine systems require wind speeds of 8 miles per hour to get the ball rolling, compared to just 2 miles per hour for an aluminum isogrid